Welcome to Tessel Bytes, where we serve you GIS in small bites. Today I'll be covering multivariate clustering in ArcGIS Pro. The mapping cluster tools found under Spatial Statistics Toolbox perform cluster analysis to identify the locations of statistically significant hotspots, cold spots, or spatial outliers. Such tools are useful when action is needed based on the location of clusters or when we are looking for potential causes of clustering, such as cause of a disease outbreak. We can find a list of clustering tools, but for now we will delve into the multivariate clustering tool that finds natural clusters of features based solely on the feature attribute values. For this demo, we will explore the data for COVID cases in Texas at county level and some of the possible vulnerability indicators such as older population, population density, vaccinated population, percent smoking population, house crowding based on number of people in a house, and change in pollution levels during COVID period. Let's understand different parameters as seen in tool interface. Here the input feature is the feature class for which the clusters will be created. It can be points, lines, or polygons. We will give a name to the output feature class. Under the analysis fields, we will find a list of fields that will be used to create the clusters. These fields must be numeric and should contain a variety of values. Fields with no variation will be dropped from the analysis but will be included in the output features. The data for this demo is pretty much clean, so we will select all fields for the purpose. It is important to note that usually we have a tendency to include as many fields as possible, but the results are easier to interpret and it is easier to determine the best discriminators with fewer fields. For clustering method, this tool uses either the k-means or k-medoids algorithm. Both these algorithms will generally produce similar results. However, k-medoids is more robust to noise and outliers in the input features. K-means is generally faster and is preferred for large dataset. Initialization method specifies how initial seeds used to grow clusters will be obtained. There are three options. The default optimized seed locations that optimizes the analysis results and performance. Other options are user-defined seed locations and random seed location. We will go with the default option. If you know, then enter the number of clusters, but if you leave this parameter empty, the tool will evaluate the optimal number of clusters by computing a Pseudo-F statistics. A chart will be created showing clustering solutions with 2 through 30 clusters where the largest values indicate the best performing options. We will select 4 in our case. Finally, the last but optional parameter is for the table containing the Pseudo-F statistic. The chart created from this table can be accessed in the tables section of the contents pane, which we will check soon. Now let's run the tool and dig deeper into the analysis. That was quick. We see that the tool produces an output feature class of non-spatial clusters with the fields used in the analysis, plus a new integer field named cluster ID, on which default rendering is based. The isSeed field indicates which features were chosen as seeds and used to grow the clusters. The output result creates charts to help you understand the characteristics of identified clusters. The parallel box plot chart summarizes both the clusters and the variables within them. You can hover over the chart to see more details. Points falling outside the upper and lower whiskers represent data outliers. Let's quickly discuss how to interpret the results. We can notice that cluster 3 in green has distinguishing characteristics based on attribute values. Dallas-Fort Worth area, Houston, and San Antonio areas form this cluster, and rightfully, as you see in the trend line of box plot chart, these are the counties with high COVID cases, more population density, and higher crowdiness. But it is interesting to note that the nitrogen dioxide pollution level for these counties improved the most during 2020 as compared to the baseline 2019. Similarly, we can explore several hidden but interesting patterns from any big multivariate dataset. You can also inspect each cluster's box plot for each variable by switching to side by side in the Series tab of the Chart Properties pane. With this view of the data, it is easy to see which group has the highest and lowest range of values within each variable, and you can see how each cluster's values relate to the other. Hover over the box plots to see the statistics. The second chart we see is the features per cluster. As the name suggests, we can see how many features are included per cluster. In our case, it's the number of counties making each cluster. Finally, let's check the optimized Pseudo-F statistics chart that we mentioned earlier. Here, the highest peak on the graph indicates the most effective number of clusters based on your input variables. From this chart, we notice that the F statistics associated with 3 groups is highest, but 4 that we selected would also be a good choice. I think we covered all the basic concepts for running this tool, and it is a good stopping point. This has been Tessellations, where we serve you GIS in small bites. Thank you for watching, and please be sure to visit us at www.tessellations.us. Also, subscribe and ring that bell.